Hello and welcome to One Code at a Time. In this video, what we are going to look at is the Bellman-Ford algorithm right here. We will see what this algorithm is, why it is used, and what are the applications of this particular algorithm. Moving forward, the Bellman-Ford algorithm is basically an algorithm for finding the single source shortest path for graphs with negative weights. That's the important point. That this algorithm is used for finding single source shortest path, which means that from a given source point, you can find the shortest distance to all the nodes in the graph. So if you want to find shortest distance from some given source node or some master node to all slave nodes, all the child nodes, then this is the algorithm that you can use. Also, this is the algorithm that you can use even when there are negative weights in the system. That is the important thing. Because if you know, you can also use Dijkstra for finding the shortest path from a given source to all the nodes in the system. But this can be used even when there are negative weights in the system, whereas Dijkstra cannot be used. Before I move forward, I would like to give credit to Cakes and ChatGPT for helping me in creating this presentation. What is the Bellman-Ford algorithm? See, basically, the Bellman-Ford algorithm is used for finding shortest paths from a single node. This is what I already told you. I also said that it works on graph with negative weight edges. This is something which I also informed. The only thing is that unlike Dijkstra, the Dijkstra algorithm could not handle the negative weight edges, whereas this algorithm can actually handle this problem. And that is why it's important to see how it works. What are the key features? One of the most key feature is that it can handle the negative weight edges. Remember, it cannot handle negative weight cycles because if your graph has a negative weight cycle, what it actually means is that starting from some point A, you can actually, so if it is a point A, you can actually go in a cycle and come back to A such that your cost has decreased. So if this is possible, then you can run infinite loops and you can get the minimum cost. Your cost will be minus infinity. So that is actually not possible. So if we take that into consideration, then yes, it is not possible. It is applicable for negative weightages, but not for cycles. The time complexity is V into E or big O of E into E. We will see how that is. And it is applicable for both directed and undirected graphs because if there is an undirected graph, what we can do is we can simply convert it into a directed bidirectional graph. Also, it can detect negative weight cycles because again, the fact is that if this algorithm makes actually runs on the principle of relaxation on finding the minimum each and every time. So if there is a negative weight cycle, like I said, you are going to get minimum weight each and every time you complete a cycle. You come back, you will get a minimum weight, then it will decrease further, it will decrease further. So it can detect negative weight cycles because if it is able to, just reduce the cost multiple times, and this multiple is actually greater than the number of vertices in the system. If it is able to reduce the cost more than three times, then it definitely means that there's a negative weight cycle present in the graph. Okay. Moving ahead. What are the algorithm steps? Let's just see this. The algorithm is pretty simple. It's pretty straightforward. What it says is that you first initialize the distance of the source to zero because you are at the source. So the cost to reach the source is zero. And initially, just initialize all of the vertices as infinity. That the current distance is infinity. Now what you do is that you have to relax all the edges v minus 1 times. This is important. If there are v vertices in the system, you have to do this operation of relaxation v minus n times, v minus 1 times, sorry. Basically, what you have to do for each edge u and v present in the system, what you have to see is that if u, if distance to the v actually is greater than the distance to the u plus whatever is the weight from reaching from u to v. Then you have to update the distance of v. That's the important thing. So for each edge, what you do is that if your cost to reach the node v is actually greater than the cost to reach the node u plus the additional cost to reach the node v from the node u, then you are going to update it. And you're going to do this how many times? You're going to do this relaxation operation v minus n times for all the edges in the system. Okay? So if you do this v minus n times, v minus 1 times for all the edges, then what you can say is the final distance matrix that you are going to get is going to get is going to contain the minimum distances from the source to all the destination. Again, if there is a negative weight cycle, then you can relax it even more. Like I said, if there is a negative cycle, then you can relax it infinity times. So the only check is that even if after v minus 1 times you are able to relax it, then it means that there is a negative weight edge cycle present in the system. So if even after resolving it for v minus 1 times, you are still able to relax it, then it means that there's a negative edge cycle present in the system. Let's look at the pseudocode in Python. The pseudocode is again very simple, that you initialize all the distance to 0 and then mark the source to all the distances to infinity, sorry, and then initialize the source distance to 0. Then like I said, that what you can do is that for all if there are v vertices in the system, then you have to run this operation v minus 1 times, because we can relax on the basis of every node, so that on the basis of every other node. So for each edge in the system, u, v, and w, let's say the u, v, and w means there's an edge from u going to v with a weight w. So for each such edge given in the code in the system, what you do is that you check the distance. If the existing distance to reach v is actually greater than the distance to reach u plus the extra cost to reach from u to v, then you have to update it. And this you have to do v minus 1 times. Okay. So this is the code that will give you actually the cost matrix, the minimum cost matrix for from source to every other node in the system. Okay. Now, even after this, if you are able to relax it even one more time, then it means that negative cycle is present in the system. That's the whole thing. This is the same code written in C. I have tested this on Geeks Geeks, and that's why I have mentioned the credits as well, that this is taken directly from GFG. Again, you can see it's pretty straightforward, that initially you initialize the distance to infinity, and then what you do is that you initialize the source to 0. Uh, this line over here, which I highlighted by mistake, is actually not. It was actually the part of the requirement from GFG, that if there is no solution, we have to return this vector, but you can ignore this at the moment. What you can focus is that initially distance is initialized to infinity and the source distance is initialized to 0. What you can do is that I'm doing it for v minus 1 times, and basically I'm doing it for v times from 0 to v minus 1. That is total of v. Note that if I can relax it, I'm going to relax it. I have taken this node u, node v, and the weight from u to v. And here I have checked this condition. Can I relax it or not? If I can relax it, I'm going to relax it. But I have to relax it only v minus 1 times. Okay. Now, what will be my Vth attempt? If my first attempt is at index 0, it means my Vth attempt is at I is equal to v minus 1. So, if I can relax it even at this instance as well, then it means there is a negative weight cycle and I'm going to return no solution. That was the basic solution for this. Here is an example graph for this. This is a very basic example. You can see that your source node is 0 and Then there are four other nodes, and there is this connection. There is a negative weight edge present in the system, and Bellman-Ford can actually handle that. It cannot handle the negative weight cycle. So what it does is it outputs the distance from 0 to every other node as follows. For 0 to 1, there is just one path, and that's right. From 0 to 2, there's again just one path here, because if you go here, then there's no path from here. So from 0 to 2, there's also one path. From 0 to 3, let's see, 0 to 1, 0 to 2, 0 to 1 and 1 to 3, this is one path. The second path is 0 to 1, 1 to 2, 2 to 4, and 4 to 3. Now, if you check this path, if I check, what you can see is the cost is 5 plus 1 plus 1, 7, minus 1, 6. Whereas, if I check the other path, then the cost will be 5 plus 2, which is 7. So again, I'm going to pick this path because it is the minimum. And again, similarly for 0 to 4, again, I'm going to pick this path. So this is how it is working. Similarly, this example is for a negative weight cycle. Here, if you check, a negative weight cycle is present. The cost is 5, minus 6, and minus 2. So the total cost is actually minus 3. And because of this is a negative weight cycle. Now, if you see in this, if you see, you can actually go around this loop infinity times and the cost will reduce even more. So if I go from 1 to 2 to 3 to back to 1, my cost will be minus 6 plus 5, which is minus 1, minus 1, minus 2, minus 3. So the cost is minus 3. But why should I stop here? Let's take one more loop. So it will be minus 3 and minus 6, which is minus 9. Minus 9 plus 5, which is minus 4, minus 4, minus 2, which is minus 6. So the cost reduces again, minus 6. And it will keep on reducing. It will then become minus 9, then it will become minus 12, and so on. It will go like that. So there is no solution to this. What are the application? This is the most important part. Again, since this is actually an algorithm for finding the shortest path from a given node to every other node in the system, it is actually used heavily in network routing protocols, which is again one of the most interesting and common use case for this problem. Then it is also used in currency uh, arbitrage detection, and it is also used for distributed systems for pathfinding. These are the common use cases. Let's go to the summary. Summary is that Bellman-Ford is actually helping us in finding the shortest path in the graph with negative weight edges, but not cycle. Important thing to note is that since I was relaxing v minus 1 times and every edge, the cost is actually O v into E. It detects negative weight cycles. It cannot solve it, but it can detect it. Also, it is more versatile than Dijkstra, but it is slow. So that was the sum. So with this, I guess we have covered the Bellman-Ford. I would also like to thank Geeks for Geeks and ChatGPT for content, and SlideScope for giving me the template to create this presentation. Thank you.